I'll give you time to copy it down and we'll talk about it. It says, if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. Remember, a proportion is one ratio equal to another ratio. And so if I cut this triangle here, I didn't label it, so let's quickly label it. We'll just call it triangle ABC. If I take this triangle ABC and I draw this parallel line in there to this side, so these two lines are parallel, then this segment and this segment, okay, are going to be proportional to these two segments. Okay? And so we can say A is to B as C is to D. And so when we say A is to B, we mean the fraction A over B equals C over D. Okay? They're proportional. No matter where that parallel line is drawn. So I do that parallel line here, so these lines are parallel, then these two segments, these ratios, A is to B as C is to D. They're still going to be proportional. Okay? That's what the side splitter theorem says. Now, how do we know that happened? I don't know how we knew that happened, but some smart guy a long, long time ago realized that that relationship was true in all triangles. No matter what the triangle looks like, no matter if it's a right triangle, a non-right triangle, or whatever, if we draw a parallel line in that triangle, cutting two sides of that triangle into segments, then those segments are going to be proportional. Okay? So it makes many of the problems they give you a lot easier if you remember that they are proportional. Okay? So in other words, we don't have to say the little triangle is to the big triangle meaning the whole side. We don't have to say A is to A plus B as C is to C plus D. Oops, there. That's true also, but we don't have to do that. Because these are proportional, these are parallel, I mean. Because these lines are parallel, then these segments are going to be proportional. Alright? Now, that got tricky last semester because we did problems that looked like this. Okay? And some of you wanted to say, well, 6 is to 4 as x is to 12. The problem is, in this fraction, x and 12 are whole sides of triangles, aren't they? X is that whole side of that small triangle, and 12 is the whole side of this big triangle. Okay? And 6 to 4, 6 is the whole side of the little triangle. 4 is just part of the big triangle. And so last semester, in the first part of the chapter, we did problems like this, and that 4 we want to put in there, but we can't. Because the other fraction was whole to whole. Well, in this problem, it's part and part in each one. Okay? It's part of the long side, part of the long side. Part of this side, part of this side. Okay? Now, we could say that it's A is all of that little triangle. I agree with that. But on the other side, C is all of that side, isn't it? And so again, we're being consistent. We're saying all of the little triangle to part of the big triangle. All of the little triangle to part of the big triangle. So our ratios on both sides of the equal sign are still set up the same way. And that's the key with proportions. There's, I won't say infinite ways to solve them. There's not infinite ways. There's a definite finite way of doing that. But there's multiple ways of doing it. Always. There's always multiple ways to write a proportion. The key is you have to be consistent on both sides. However you set up the left half of the proportion, you have to set up the right half the same way. corollary to the side splitter theorem. I'll read it and then I'll pause so you can copy it down. It says, if three parallel lines intersect two transversals, then the segments intercepted on the transversals are proportional. Just a reminder for those who were in here last semester, and especially for those who were not. A corollary is just a statement that adds more information to a theorem. And so it's like a second part to that side splitter theorem. It's just giving us more information about it. It's extending it. The theorem talked about a side of a triangle being parallel to another segment drawn within that triangle. This is extending it to three lines. If all three of these lines are parallel, then these segments between these parallel lines are going to be proportional. They won't necessarily be equal, but they'll be proportional. Again, this is very similar to one we learned last semester, in which we said if these lines are parallel and these segments were equal, so we said if these parallel lines cut this transversal into equal segments, then that's going to cut every transversal into equal segments. So this distance here will equal this distance here. So no matter where I draw that transversal now, I know those parallel lines are going to cut them into equal pieces. So if I knew this was 15, then how long is this one going to be? 15. Okay? And so they're very similar, aren't they, these two theorems? The difference is, in this case, these lines had to be equal distance apart. Okay? Had we measured these lines, they didn't talk about it, but that's what it was saying. If we measured these lines, the distance here would have to equal the distance here. And the one we're talking about today, that's not true. These lines are not the same distance apart. Okay? But these segments, A and B and C and D, are still going to be proportional. So any transversal I run through there, if I put one through here like this, and I label this EF, then A over B equals C over D will equal what? E over F. Okay? That's the difference between the two theorems that we talked about. Alright? So I don't know if it's helpful or confusing to you, but I want to try to clarify the difference between what we've already done and what we're doing new. Okay? So I want to make sure you understand that. Didn't look like much of an arrow, did it? Okay? Actually, I was just trying to point out what I try not, because I'm recording it, it's not taking a picture of me pointing at things. It only records what's happening on the board. I try not to just talk about things without touching them or pointing to them or highlighting them, so that when you are watching it, you'll know which ones I'm talking about. The triangle angle bisector theorem. I'll read it and I'll let you copy it down. If a ray bisects an angle of a triangle, then it divides opposite sides into two segments that are proportional to the other two sides of the triangle. All right, what is this saying? Well, it's saying that if this segment, this line, this ray, whatever we want to call it, is bisecting this angle right here of this triangle into two equal pieces. That's what bisect means. Cuts into two equal angles. Okay? So it's cutting this big angle up here into two angles that are equal to each other. Bisects it. Then that means the other end of that line is cutting this third side into two pieces that are proportional to these two sides of the triangle. So that means A is to this segment as C is to this segment. And so we could write the proportional A is to B as C is to D. The key here, how do you recognize this when you're doing a problem? Is you have to notice, is this line bisecting that angle? Are they telling me that these angles are equal? If these two angles are equal, then that means they're cutting this big angle into two equal angles. So this side's going to cut, this line's going to cut this side into segments that are proportional to these two sides. Okay? And again, we probably could prove it by using similar triangles. Okay? We probably could prove it that way, but we don't have to. Okay? They gave it to us. It works. We don't have to. Prove anything. Okay. I cluttered that up so much it was hard to see. So there we go. All right. Any questions on the triangle angle bisector theorem? Okay, so that's it for the notes. We have a couple examples here. Applying those notes. Any suggestions on how I could solve this example number 1? Okay. And you recognize the side splitter theorem because these two lines are parallel. Good. And so how would I write it then? How would I write my statement using the side splitter theorem? 7 is to 9 is x is to 4. Okay. You know what you said the first time would still work. Okay. I encourage you not to do it that way, but it would still work. That's the nice thing. Remember, I said proportions. There's multiple ways to write them down. They're all going to be the same. That's one of them. She originally said 7 is to 9 is x is to 4. I would stick with splitting that side up. And she said, secondly, that 7 is to x as 9 is to 4. Okay? And that's the way I would go. So we would say cross products, 9 times x equals 7 times 4. Now, had we gone the other way, she said 7 is to 9 as x is to 4. What would cross products give me? 9x equals 7 times 4. Same thing I had here, isn't it? You see what I'm saying, though, with proportions? There's lots of ways to set up the original. We're still going to get 9x equals 28. Okay? When I encourage you to think of it one way, though, it's usually because other things are coming down the road that when we consider it that way, and we always think about it that way, we're better prepared for the next concept. Okay? And in this case, it's not that I see something coming down the road. It's just that the side splitter theorem itself compared them this way. 7 is to x as 9 is to 4. Okay? And so if we stick with that theorem, then we would write it the way we did right here. And so x is going to equal 28 divide 9. Sorry, 28 divide 9. And so if they say round to the nearest tenth, that would be 3.1 repeating. It's 3 and 1/9, which is actually equal to 3 and 1/9. And remember, I think I showed you ninths. 1/9 is 0.1 repeating. 2/9 is 2 repeating, 3/9 is 0.3 repeating. Some fractions like that have some interesting can't think of the right word for it. Yeah, that's not quite what I'm trying to say, but you know what I'm trying to say anyways. They're kind of interesting. They have a pattern, they have a repetition, they have something that's unique about them. And so when we get them, I try to point that out to you. Okay? And so 1/9 is one of them. Or 9ths, I should say, is one of them. Okay? Number 2. Example number 2. Oh, this is... This is confusing. This is not side splitter theorem, is it? We did actually do this today when I reminded you of what they did earlier in the chapter. Okay? Any suggestions how we could set this up? 7/x, 8/12. Okay, I'm going to go ahead and write that down. I'm going to do it in red, though, because it's not correct. Okay? The reason I wrote it down, though, and I'm going to put a circle with a line through it, meaning don't do that, because that's what you're going to do. I'm going to tell you right now, that's what you're going to do. It's not I'm trying to get you to get that one wrong. It's I'm trying to get you to understand the difference between these two problems. This is only part of a segment, isn't it? 8 is the full length of this side, and 12 is the full length of this side, and 7 is the full length of that little triangle there. Right? And 8 or x is only part of it. And so the question is, how long is this whole segment? 7 plus x.
So 7 plus x over 12 and then
7 plus x over 12 and 7/8. Okay? I certainly could live with that. I normally try to get you to go 7 plus x over 7 and 12. I went, long side over 8. I went the full length of the big triangle to the full length of the little triangle, so I'm going big to small is my ratio. Big triangle to little triangle. So over here I'm going to go big triangle to little triangle. Either way, I'm going to get 8 times x plus 7 equals 7 times 12. Okay? I would get the same thing over here. It'd be exactly the same thing. Okay? You know, I have to do both of these. I confused some people earlier in a different class. They did something like this. They thought the two had to go together. No, I'm just showing you there's 2 ways to set it up to get the same second line. They're the same second line. And so now we have to solve. Some people want to distribute. You can distribute. Or I could divide right now by 8. My 8's are gone, leaving me x plus 7 equals. And if 4 goes in there twice and 4 goes in there 3 times, so I get 21 halves. If I subtract 7 from both sides, I get x is equal to, that's 10.5 minus 7, which is 3.5. Oh, really? Okay. Well, we'll finish this tomorrow. Just one more example. And then